The topic of this lab was basically finding the mass of a black hole. The basic concepts behind this lab. So the purpose of this lab was basically to demonstrate the gravitational force formula. We looked at the trajectories of the parallel and perpendicular components that make up the gravitational force, the trajectories of the star. So we were given one star and a black hole. We had to change our code and write basically our code to find the mass of the black hole and the star that it is orbiting. The star's mass here is 2 times 10 to the power of 30 kilograms. The formulas that we used was mass of F gravitation, which equals minus g mass of black hole, mass of the star, divided by the distance squared. Where if we wanted the vector component, then we have to find d hat, which is a unit vector, which is basically found by the distance vector divided by the magnitude of the distance. So the perpendicular component of force would be the magnitude, and the parallel force is basically the distance. The coding for visualization and graph initialization was given by here was basically where I initialized my graph. So like this was basically given to us. And then afterwards for placing in the coding system properties and initial conditions, the mass of the star is here, the gravitational constant we all know, and the time interval between imported data points for me was 8,640. So to calculate the velocity from the data, I created two lists. One was x velocity and one was y component of the velocity. One basically held the calculated x components and one was the y component. So I made two vectors. And then I set my IDX equal to 0, and it would change and it would go through all of the loops to basically calculate the x components and the y components of velocity given different data points. So my calculation loop here would iterate over all of the data values, and it would use the velocity components to basically define, as you can see here on line 149 through 161, to define the initial and the final velocities through the given matrix to the given vector that I created here. And then to compute the initial and final momentum vectors, I just did velocity initial times the mass of the star, which would give me the initial momentum, and then the final momentum. To calculate the star's change in velocity and change in momentum, I would do v final minus v initial for both. So to calculate dp over dt, it would be delta p over delta t, and then to f net is equal to delta p over delta t. And then to calculate the parallel, basically we would take the norm of the initial velocity and then the magnitude of p final minus p initial, and then divided by delta t again, and that would give me the parallel component. And then I use Newton's second law to calculate the net force, and then for the perpendicular component I did the same. To calculate the mass of the black hole, I used basically this formula here, which is the magnitude of F net times the magnitude of the star times the position divided by the gravitational component times the mass of the star. To update the current position and velocity, again, I used my vector that I had created before, and that basically would give me a list of values to calculate the mass of my black hole. To actually find the mass of the black hole, I took all of the values that were given and I averaged them all out to find an average mass. And I got my value to be 2.19 times 10 to the power of 36. I rearranged the gravity force formula to find this mass, as you can see on the code on the right. My F net was 1 times 10 to the power of 31. My F net parallel and perpendicular, as you can see, were different, and they were 4.9 times 10 to the power of 29 and 1 times 10 to the power of 31. When it comes to the question that was asked, here, as you can see, the magnitude for the momentum was different for the magnitude of the force that was given in our data points and during our calculations. Therefore, since the magnitude of momentum is not equal to the magnitude of force, that would make both of them different. Even though here we can see that you can calculate the parallel component is supposed to be equal to the parallel component of the force, and here the perpendicular component should be equal to the perpendicular component of the force. In our system and in our situation, that they wouldn't be equal. That's because the magnitudes were not the same. So if we imagine that the black hole, whose basically mass we found was removed, and then a different black hole was placed in the same location, the motion of the observed star would be unchanged, and it would be affected only by the gravitational force of the new black hole. So here, as you can see, we can tell the difference because the gravitational force that the new black hole with a different mass would have on the star would be different. This is because, as you can see from the formula, gmm divided by r squared, the motion of the star might be the same, but it's possible to tell the difference because the gravitational force would have changed.